Hello world, it's Dr. Doherty from Abilene Christian University. Let's talk about relativistic approximations. They make some problems easy, they make hard problems possible, and physics and science would not exist without the ability to approximate good things. So let's talk about how this works. Having a summary like this is very, very important for a modern physics class. So, how do we do it? Well, I'm going to make a couple of columns here. So let's start off with something that is just non-relativistic. I'll do that in blue because it's cold. So I'm going to have a couple of conditions. What do I know about this thing? Well, all right. The velocity is much, much less than the speed of light. I think we can all agree on that. In that case, gamma, my relativistic factor, is about 1. And if you Taylor expand it, you can get a few more terms out, but I think 1 is going to do us for today. And I'll leave room for one other thing that will come up in a little bit. And so what do I know about these cases? Well, so let's calculate things like kinetic energy. So, well, ask any engineering physics 1 student. I've got that kinetic energy is 1/2 mv squared. Now, to put it in a form that's also useful to us, well, let's go ahead and write down momentum. All right, P is equal to mv. Just by inspection, if I take that P as mv and I want to write kinetic energy in terms of momentum, P squared over 2m, and it's pretty obvious that that's equal to 1/2 mv squared. This form tends to be really useful when you're doing modern physics. All right, now let's get a little weird with it. So let's talk about total energy. By total mechanical energy, I would mean kinetic plus potential. Now we're going to assume that we're living in a world that has no potential. You just have to add those terms on later yourself. So my total energy would then be my kinetic energy. Except I'm going to talk about things that are relativistically correct. So here in a moment, I'm going to be adding an mc squared mass term. And that's almost like a potential energy. It's the energy that I have just by virtue of having mass. So I'm going to write this as my total energy is my kinetic energy, p squared over 2m is the form that I like, plus mc squared. And we'll talk about this mass as kind of like being our potential energy term. Now, I'm going to do one thing to this to make this even easier to deal with because life is hard. Let's not suffer needlessly. I'm going to notice that if I take my p squared over 2m term and I multiply numerator and denominator by a factor of c squared, I can write this as pc squared over 2mc squared plus mc squared. And that form tends to be really, really useful when I'm dealing with particles because I can look up the mc squared of the particle and I have p in my right units of energy per c. Okay, so what have I learned about this? Well, let's talk about one more thing. Compare then momentum with mc squared or pc with mc squared. Well, p is mv, so we can tell, I'll switch to purple here, this term right here would then be equal to a mvc quantity squared over mc squared. Okay, the masses would cancel out. I'm going to have a v squared, c squared. The c's are going to be gone. So what I've got here left in this term is just going to be a 1/2. So this term, just being kinetic energy, is 1/2 mv squared. How does that compare with our mc squared? Well, v is much, much less than c, so 1/2 mv squared is much, much, much less than mc squared. And this is going to be our important thing to keep track of. How do I know when I'm non-relativistic? Well, I know that my momentum term or my kinetic energy term is much, much less than my mass term. So some new restrictions that we can put on here. I can say that my kinetic energy is much, much less than my mass energy. Or, if you prefer, I could say that my momentum, PC, is much, much less than mc squared. All right, let's now talk about the hard case. This is the case where I don't get to make any approximations. I cannot say that these are much, much less than mc squared. They're within a few orders of magnitude. I cannot say that v is much, much less than c. I cannot say that gamma is about 1. So I can't make any of those nice, simple distinctions. Okay, well, what about kinetic energy? So we know that my kinetic energy is equal to gamma minus 1 times mc squared. I know that my momentum is equal to gamma mv. And we remember that all these have to reduce down to the classical non-relativistic in the limit of low velocity. So if I Taylor expand gamma, I get a 1 plus 1/2 v squared over c squared. And when I write that in this term, it gives me 1/2 mv squared. In the limit of slow velocity, gamma approaches 1, p approaches mv. I have two equations for energy that are helpful to us. So I've got gamma mc squared. Sometimes that's an easy way to find what I want. I can also relate energy and momentum and mass by doing E squared equals PC squared plus MC squared quantity squared. Now here, in my non-relativistic case, I'm saying this term is negligible compared to this term. Well, in my relativistic case, I can't simplify it. I'm stuck with both of those things. I've got to do extra hard work. Now, if I start going extremely fast, life actually becomes easier again. So I'll do this in red because we're going really, really fast. We've got a really hot particle. So ultra-relativistic. Now, in this case, we can approximate our way to victory. So what have I got? Well, V is going to be approximately equal to C. So maybe it's 0.99 C or 0.999 C, but at least within the ballpark of C. I also have that gamma is probably going to be much, much greater than 1. Maybe it's 10. Maybe it's 100, maybe it's 1,000, but it's at least an order of magnitude bigger than 1, and that's going to simplify some things for us. So let's look at my relativistic kinetic energy. So suppose that gamma is much, much greater than 1. Well, I can neglect the minus 1 part, so my kinetic energy is equal to gamma mc squared. Well, gamma mc squared is just my total energy. So all of my energy, approximately, is kinetic. That's interesting. My momentum term is going to be large, in fact, much larger than my mass term. So as my momentum grows and grows and grows, this term becomes more and more and more negligible. So to relate my momentum now, I'm going to have to say that my energy is approximately equal to P times C. Because when I get to neglect this term, I can square root both sides, and I've got E is approximately equal to PC, which was also approximately equal to K. Now, this is the good life where things are really, really, really simple. My energy is all kinetic, it's all coming from the momentum term, and I'm completely neglecting the mass term. Notice, in fact, that nothing here in this column has an explicit M dependence. Well, yeah, E is gamma mc squared and P is gamma mv, but in the ultra-relativistic limit, this mass term becomes negligible, so it's all energy and momentum. Okay, keeping these facts around really, really helps when you're doing modern physics problems or atom smasher type problems. Notice which frame you're going to be in. So to write down our sort of final fact here, in this case I've got PC much, much greater than mc squared, or my kinetic energy much, much greater than my mass energy. So if I give you a new problem to solve, the first thing you want to do is figure out which case are you. Compare the momentum or the kinetic energy to mc squared. If it's much, much smaller, you're non-relativistic. If it's much, much bigger, you're ultra-relativistic. Then your life is easy. Otherwise, you've got to deal with the relativistic case and deal with everything put together. Okay, I hope this summary helped out a lot. I'm going to leave you with one last question that I hope we get to discuss later. So, what happens when things start to go really, really, really fast? Well, at the speed v equals c, gamma becomes infinity. So wouldn't these equations then imply that it takes infinite kinetic energy and infinite momentum and infinite energy to go the speed of light? So my question, at least especially for my students in class this semester, at v equals c, gamma equals infinity. So I've got infinite energy, infinite kinetic energy, infinite momentum. So going the speed of light is impossible because I don't have infinite energy to give something so that it can go that fast. So the question then, if going the speed of light is impossible, how does light go the speed of light? Good thing the answer is staring us in the face. There's a beautiful little loophole in these equations that we can take advantage of. Well, hope we get back to answering that later on. Thank you all for watching. Happy relativistic approximating, everyone.